All right, last class for today, and I want to talk about one more interesting yet challenging problem about Tower of Hanoi. It's going to help you about recursive thinking and also some Java coding to discuss as well. That's something we'll do. And then I'll do a wrap up of the course as well, just to summarize about the topics we have learned up to now for this term. Right? And then if we got any time left, I can also take your questions, maybe about the exam or anything else about the course. Right? We'll try to see how much time we're gonna manage to get today. We'll see. All right, reminders about your lab number 5. Just make sure you submit by midnight today. And don't forget, you gotta study for abstract classes, interfaces for your exam. And also, tomorrow, maybe shortly after lunchtime, I'm also going to release a solution to lab number 5 to you as well. You can also take a look. Hopefully that will help your understanding too. Okay, just don't forget to submit in time. And for your programming test number 3, I released the result and feedback. If you want to go over any parts, let me know. About your regrading request for programming test 1 and 2. Now that we finished grading all the programming tests, so now the TA are focusing on those. I'm hoping to give you some feedback about your regrading request very soon. Okay, hopefully by the end of Friday, I'm hoping. But I'll keep you posted. For those of you who submitted regrading requests, you can expect some email from me pretty soon about the result. I do have office hour, 7 p.m. tonight, if you want to speak to me, or maybe on Thursday, 3 to 5 p.m. as well. It's going to be in person, but if you want to connect me through Zoom, it's possible, but I'll give priority to students showing up in person. We'll see. And then the review session is going to be Zoom, 3 p.m. on Friday. Tentatively can be 1 hour, but if you guys got more questions there, I'll be happy to stay maybe for up to 90 minutes, 2 hours. It's okay, but it's really up to you guys. And the review session, or like a tutorial session I gave on recursion on Sunday. So I put all the material, source code, solution project, problem description, everything on the lecture side. Take a look. I think that can also help you understanding recursion in general. It's going to be very beneficial, not just for this course, but in 2101, next semester. You're going to need recursion very badly, right? That's something you definitely want to master, hopefully, before the next term. All right, any question about the course? Yes? You know, for lab number 5, I don't really have a video, but at least I can give you guys the complete source code this time. So go over the source code, and if there's any part you want me to go over with you, drop by office hour, we can do that too. Yeah, I wish I had a video. All right, at least the source code, yes. Yes, for sure. So the review session over Zoom, I know some of you might have some clash with the session, that's okay. I'm gonna record the session for sure. I'll try to post it maybe before I have my dinner on Friday. How about that? Maybe before 7 p.m. I can do that. All right. So you guys can still take advantage for some last minute study on Friday night and Saturday. I know the exam is Sunday morning, right? Please make sure you go there in time. All right. All right, quick recap from last Thursday, okay? So the only thing I want to point out to you would be, of course, we solve more recursion problems on the string. For example, let me just see, okay. Yeah, we'll talk about the reverse of the string and also the number of occurrences. Not much to say, just go over the recursive thinking phase to see how you can plan for the sketch and also see the Java code, right? That's all I can say. You gotta review the details. And we spoke about this very important pattern. If you want to make a recursion, make a recursive call on an array, conceptually, you're basically creating a subarray with strictly less elements there, but it's going to be very time-consuming because you're going to use a loop and also waste of space. For every recursive call you're making, you have to create a subarray. It's going to be waste of space. So in 2101, next semester, we're going to analyze code fragment like this to see, even though that's correct, but it's not efficient. That's something we'll have to talk about in another course. So what we do instead is we need this pattern here. We do call by value. So for every level of the recursive call, you're basically passing the address of the same array. So we don't create any array. And then the way we try to create a strictly smaller problem is by using indices. So these two integers specify a range of elements we can look at in the array. So we start with the range that's going to cover the entire array, and then we do, for example, from +1 is effectively going to reduce the range by one element, right, and etc. And when we solve the Tower of Hanoi problem today, we're going to see the same pattern again. Right? It's a very interesting problem to actually study as well. Quite a classic one. All right, so please, for your exam, make sure you review this pattern here. And we spoke about all positive and also is sorted. I just want you to remember, whenever you got some empty collection, that's an empty array, should you return true or should you return false? Right? It depends on the nature of the property you're checking. Right? That's something you can also refer to the notes from last time. Right? I'm going to let you do that. All right, and then that's it. And of course, we did some like a tracing in this kind of format. I'm going to do that for sure for Tower of Hanoi. I think for the Tower of Hanoi, the Java code itself is incredibly simple. You got less than 10 lines to write. However, to really understand the insight about the clever manipulation, you need lots of tracing and lots of visualization. That's something I'll try to do as much as possible for you today. All right, so that's about the tracing we did. Okay, and then any question from last time, from last Thursday? All right, that's good. So we can dive into the new problem. All right, Tower of Hanoi. All right, let's look at some slides. And I also make available the source code, the Java solution on the web. I'm going to show you how you can use it. It's quite a fun tool to actually experiment. Okay, I'll get to Java code in a moment. Let's see what the problem is. Okay, for those of you who don't know, that's one example of the problem. Okay, basically you got 3 sticks over there. We call PEG, P-E-G. We got 3 pegs over there, and you can see the disk over here. I got 8 disks over there. The way you arrange the disk will be from the smallest on the top all the way down to the largest at the bottom. It's got to be in this order. And how does the game play? Okay, so here I say given 8 disks. In general, it can be n disks. N can be either 1 or 0 or 3, 8, or even 64. I'll talk about the magic number 64. Okay, I'll talk about it. All right, so you got 3 packs over here, and then here's the rule. Whenever you want to move, you don't really move the entire tower. You only move 1 disk at a time. Whenever you put a disk into a pack, you cannot really put anything that's larger on top of something that's smaller. Okay, so these are the only 2 rules you have to follow. Our goal is this. I want to move, for example, all these 8 disks from one pack into another pack. Of course, there will be many intermediate steps. All right, that's the problem. And of course, very simple definition here, but let's get some intuition. Let's try to solve Tower of Hanoi right away. All right, let's now do that, okay? I got 3 examples to show you. Either there's only 1 disk, or you got 2 disks, and also we got 3 disks. All right, let's now do one by one. When you only got 1 disk, that means I put this, I only call A. So A, we assume is always the smallest, okay? If I only got this A on pack number 1, I want to move that to pack number 3. How many steps would it take? Just 1. All right, that's easy. Oh, sorry. Move it here. 1 step. Easy. And slightly more complicated would be this one here. If I somehow want to move, I cannot move 2 at one go into pack number 3 right away. So there is some very important terminology that will be the key to understanding the solution. In order for me to move the entire tower into P3, you can see here we say go from P1 to P3. The remaining one is something what I call intermediate pack. Okay, just remember that terminology. We're gonna need an intermediate one for us to define some solution recursively. Okay, I'm gonna make an annotation here. Just say P2 over here. This is something we call intermediate. And the tricky bit is P2 is not always the intermediate. Intermediate can be P1 or can be P3. It depends. All right, it really depends. Let's say for now, I want to move this guy here conceptually into here. So what I would do is I may just say I can move this one here first, and then move this one into here, and then move this one here to here. So you can see I somehow use the intermediate as a jumping storm, basically, right? That's how I solved the 2-disk problem, which is also not too bad. And now things will get slightly more complicated, right? I'm not talking about any strategy just yet, all right? I'm just trying to show to you how you can play with it. How about this one here? 3-1, okay? So let me try this. Maybe I would say I can put this one here, this one here, this one here. So what I have done here is kind of halfway. I managed to move the sub-tower, which is a strictly smaller problem, from here into something that's intermediate. Because I want to move from P1 to P3, so I try to move some strictly smaller tower into the intermediate pack first. After this, I'm just going to move this bottom guy into here. I'm not done yet. Think about I got another half of the work to do, which would be I need to solve another strictly smaller problem here. I want to somehow move this guy here from P2 into P3. And now, which one will be this intermediate pack? P1. Whatever that's not the origin or destination should be the intermediate, right? That sounds insight. All right, so how do I do it? So I can move this guy here. I can put it here, and then put it back. Oh, sorry. That's a bit tricky to really move that. There we go. All right, that's a play. And of course, for those of you who might be interested, feel free to try 4 disks. All right. Now, I want to show you something quickly on Java. So this is how you can play with the code. The code has been implemented for you, so all you got to do is play with it. Okay, I'll show it to you. So if you go, this project is already on the lecture site. It's called Tower of Hanoi. And you will see under the model package, is actually a class called recursive helper method. So there are 2 methods there, which I'm going to explain to you. So you can see only 1 line for the first method, and for the second method, also not many lines, only that. So pretty concise definition, but we're going to go over that. And how do you run it? I created basically a console tester over here. We're going to run it, but there's another JUnit test case, which I encourage you to also take a look. I kind of show you some kind of pattern for you to kind of test console output, system.out print line. Take a look. It's going to be useful, maybe for Java programming in general. Okay, I'll leave that exploration to you. And if you try to go to the tester here and then run it, that one there is actually going to show you the solution for various problems. Let me just show you how you can read it. For example, you can see if you're trying to move 0 disk, nothing to do, empty, no step to follow. If you just try to move 1 disk over here, the program tells you you just got to move the disk A from pack number 1 to pack number 3. All right? And then the one I just illustrated is about moving 3 disks over here. That one there basically is going to, the first 3 steps correspond to what I said halfway done. And then after another one, moving the bottom one, we got another half over here, right? So there's a perfect correspondence to how I solved the puzzle, which I didn't really tell you, but I'm basically following some systematic strategy, which I'll show to you how to do it, all right? And also, as a look ahead, so I'm going to show you the strategy. I'm going to show you some legend that's associated with Tower of Hanoi, just for your information. And then we'll analyze the Java code, visualize it, we'll trace it. And there's also one more thing I want to do today, which is not going to be exactly covered in the exam. We just do some runtime analysis. I want to give you guys some flavor about part of what you're going to do in 2101, the data structure course in the winter. That's something you will have to be very careful in doing. But I can give you guys some idea about how it can be done. All right, we'll get one by one. All right, so that's about Java code. Please take a look if you're interested. Okay, some legend before we dive into the strategy. Okay, so for those of you who are familiar with the Indian culture, please correct me. I got very superficial understanding about the culture. So Brahmins, it's like maybe some workers in the temple somewhere in India. They have been carrying out some movement, so-called Sacred Tower of Brahman. That one basically is like a tower of Hanoi. The only difference is, rather than having just 1, 2, or 3 discs, they got 64. 64 discs. All right, 64. Something like this, right? You can see some worker there. They're trying to basically got 64 and trying to move from one pack into another. And they have been starting doing this thousands of years ago. They have been doing this already. And there's a legend there saying that, of course, they follow the same rule, which I just illustrated to you. When they are done, it will be the end of the world. That's the legend. So what we're going to do today is mathematically, how long is it going to take them to really finish that movement? Hopefully not that soon. I think you need to have your exam first before that happens. Hopefully, right? All right, so anyway, we'll take a look, right? That's a legend. I'm not too sure if that's really true, but we're going to have a critical mind about it mathematically today. Okay. So let's now take a look. Let's now talk about the strategy first. So there will be 3 phases, like 3 critical steps. Let's say you have n disks. You want to somehow move the n minus 1. So think about n minus 1 is strictly smaller than n. It's a strictly smaller problem that we want to solve. So think about what I did earlier was this. So phase number 1 goes like this. I want to move this guy over here, ultimately from P1 to P3. Phase number 1. I want to move everything but the bottom one. So this strictly smaller also tower, I want to move it from P1 to the intermediate pack P2. So after all these 3 steps, I will achieve that. Okay, so think about this here is the after phase number 1. Okay, so we start with this. After some step in the middle, we're going to reach the end of phase number 1, in which case we have moved the sub-tower from P1 to the intermediate pack. Okay, that's phase number 1. And for phase number 2, according to the slides, we're going to move the bottom one, the largest one. All right, the way to move it is, so after phase number 1, we got this. So we're going to move this bottom one here to the destination, which means we got this. So this will be the start of phase number 3. For phase number 3, you can see here we got the sub-tower here, but it's in the wrong pack. So we got another problem to solve, which is strictly smaller. We want to move this sub-tower from P2 back to P3. And it will take certain steps over here recursively somehow, and this will be the ultimate solution. So 3 phases. Phase number 1, phase number 2, and phase number 3. Okay, but I'm going to dive into details more. But conceptually, just remember you got 3 phases for the Tower of Hanoi. It's a very systematic strategy for you to follow. You can solve any arbitrarily large n from 1 until 64 or even larger. But we're going to analyze at the end how efficient it is, right? We're going to see at the end. But let's understand the correct solution first. All right, let's now go over the Java code. Okay, Java code will take quite a bit of visualization, which I think that you guys should really understand first. All right. So the Java code is going to be the Tower of Hanoi. That's the method. And this will be the public version. We simply represent the disks over here by a string array. So think about if this conceptually is the tower. You can think about that's the top elements, that's the bottom one. So convention is the smallest to largest will go this way. And for the array, the smaller to largest will go this way. That's our convention. That means over here, think about when we do the recursive call, we're going to say from and to, like the pattern that we learned from last Thursday. So think about this one here is the from, let's say, for example. And then from is going to correspond to, for example, the top. So you can think about from here is from here. Okay, just one example. And then this one here will be the bottom. All right. This will be maybe the 2 index. So think about the 2 is the bottom one here. So we got from here, we got 2 over here. So there will be another special case will be the second last disk from the bottom. This one here, like a second largest disk. And that one there should be of index 2 minus 1. Okay, we're going to need it later. So this will be 2 minus 1. So think about this, another disk over here. That's 2 minus 1. Okay, so when we program in Java, we got to work in terms of the array. But conceptually, you got to see the correspondence to the tower. That's why I'm also drawing that, right? That's important. All right. And then let's now try to analyze the call over here. So in the beginning, when we call this so-called recursive helper method, let me remind you about the term. It's a helper method, but it's also recursive. So this is a recursive helper method. And call by value, we're going to pass the reference of the array. That's the same. And in the beginning, we say that we want to pass the entire tower. So this part here, you can think about what we're doing is, let's say 0 to disks.length minus 1. That's basically going to cover the entire range, right? From 0 all the way to the length minus 1, right? That means it's going to cover the entire tower. Okay, entire, from the top to the bottom. Of course, later on, we're going to, for recursion purpose, we're going to subdivide that into sub-tower and the bottom, right? That's what we'll do later. And convention here for 1 and 3, that's important, okay? So the 1 and 3 here are about the packs, okay? So here, 1 and 3 is about the packs. Think about the pack. We got pack number 1, pack number 2, pack number 3. Okay, but in Java, when we pass the value, we just pass either 1 or 2 or 3. Right? That's something to remember. So let's now think about how to interpret this recursive helper method call. We pass the disks over here, which represent the tower that we're trying to solve. And we say that in the beginning, we want to solve the entire tower from 0 to the end. That's basically the entire array as a range, or the entire tower. And where do we want to move it from and to? We want to move that from pack number 1 to pack number 3. That's how we interpret that method. All right? So I say the trickiest bit about this lecture here is to understand how the Java code itself corresponds to how you solve the puzzle on the paper. That's the most critical insight you want to convince yourself. All right, any question so far? All right, that's good. So this one is nice. And then let's now talk about the recursive helper method itself over here. Okay, it's called TOH, Tower of Hanoi helper. Again, we pass the disks over here, call by value, and we got from and to. So think about here, it's going to be from and to. Oh, sorry, let me do that. That's what I meant to draw. So from and to. So this one here really corresponds to this part of the array. I want to just, oh, sorry. Let me do it again. We don't divide just yet. From and to. Okay, from and to is actually going to cover the entire thing to begin with. Okay, that's good. And then we're going to move from origin to destination. This could be some value. And the value for origin could be 1 or 2 or 3. This one can also be 1 or 2 or 3. It depends. All right. From the origin to destination. And the two base cases should be quite straightforward. When you got from larger than 2, as we said, that means empty range. That means no disks to really move. So no step. Don't print out any step. On the other hand, when from is equal to 2, for example, if I say I just want to move this one here, so that'll be from and to just being equal to this 0, for example. In that way, I will simply say I want to move something. Okay, for the details, I'm going to do the tracing in a moment, but that's something you can also look at, right? Just remember, from and to tells you only one disk to move. So this is definitely a very important base case. So this one here tells you only one disk to move. Only one disk to move. All right. All right, let's now talk about recursive case. That's the most critical bit, right, to understand. And if you recall the strategies I talk about over here, right? Step number 1, number 2, and number 3. All right, and we got exactly that. Okay, I'm going to label them first of all. This will be number 1. This will be number 2. This will be number 3. And I'm going to visualize each one by one. All right. And one thing very important to talk about. Let's say, for example, if I want to move the entire tower from P1 to P3, in that case, the origin and destination will be 1 and 3. Right? If I want to do that from 1 to 3. And when we divide the problem, we're going to take the sub tower over here and move that recursively to the intermediate tower. Now, how do we know computationally what an intermediate tower is? When we go from 1 to 3, 1 and 3, the intermediate ID should be 2. Because 1 plus 2 plus 3 is 6. So we know that if we know the numbers for the other two, we can subtract to get the final one. All right? That's really important. So now intermediate in this case will be 6 minus 1 minus 3, which will be 2. Again, this tells you if my origin and destination is 1 and 3, I want to move from pack number 1 to pack number 3. The intermediate one for me to play with during the recursion will be number 2. Let me give you another example. What if I got, let's say, I want to move from 2 to 3. So conceptually, I want to move the entire tower from 2 to 3. What will be the intermediate one? Number 1. How do I calculate it? 6 minus 2 minus 3. I'll get 1. All right? That's something you have to also convince yourself. That's a very critical calculation. And we can do this simply because we got 1, 2, and 3 only, always. Okay. All right, so now let's take a look at these 3 over here, which is very interesting. All right, I'm going to visualize them one by one. Okay, it's important. And number 1 here, and before that, let me tell you the starting phase, the starting states. For that, let me copy this. Put here. Okay, that's what we start with. Oh, sorry. There we go. Okay, that's what we start with. And this one tells you we're going to call the Tower of Hanoi helper recursively. That's the first recursive call. Disks over here, just call by value, the same. Now, from and to minus 1. That one there tells you you're actually going to, okay, let me use a different color here. That one there tells you I'm going to go from to 2 minus 1. So from to 2 minus 1, that's the array. What does that correspond to in the actual tower? So from to 2 minus 1 is going to go from the top all the way to everything except the bottom layer. So that one there basically tells you that's this one here. Okay, if I want to make it more explicit for you, that's orange. So that's the tower I want to get. All right, conceptually. I basically want to move this sub tower over here, which will be here. I want to move that one there from origin to intermediate. All right, the origin is here. The origin is where we start from. This is the origin, so this is the destination. And the intermediate is going to be using the formula I just spoke about, right? The intermediate is going to be this one here. So what I will do is for stage number 1, I'm basically going to recursively move this one over here. Okay, let me see if I can do it in one go. All the way to here. That's what we're doing. Okay? If you get about 50% understanding, that's great. It's a challenging problem, right? It's going to take some time. All right, so that's stage number 1. So stage number 1, we have moved this guy here, that used to be here, to the intermediate one. And stage number 2 is going to be, you can also think about it's more like a base case. It doesn't require any recursive call. From there, we're going to say disk 2, okay? So this one here, disk 2, is corresponding to basically the bottom one over here, right? And also, it's basically just this part, the last bit of the array. Okay, and we're going to move that from origin to destination. Okay, how does that work? So let me just copy this one over here, and then I'll show to you. Just don't forget, stage number 2 follow after stage number 1. So what we're going to do is we're going to move this bottom disk, which is the largest, from origin to destination, right? From origin to destination, this one here, which is here and also here. Right? All the correspondence is clear. Finally, we got step number 3 here, phase number 3. This is just another recursive call. Because if you look at the end of stage number 2, we have not quite done yet. We got this sub tower over here in the intermediate pack. What we want to do is, again, recursively move it from pack number 2 to pack number 3. And in this time, when we want to go from here to here, this will be the origin and this will be the destination. Right? So the origin should be right here. You will switch. So when we do the tracing, you will see that the origin and destination are not necessarily always 1 and 3. It does change. All right. All right. So let's now try to understand the final bit over here. Okay. And from and 2 minus 1 is basically the same. So let me just use, how about purple? Okay. From and 2 minus 1. That basically tells you we're just going to consider the same range for the second time, right here. All right. And then think about that one there is going to talk about this tower here for the second time. Okay, right here. Just this tower, just for the second time. All right, you can see we consider the first time, which is the orange, the second time, which is the purple. All right. And then we're going to have stage number 3. Okay, let me copy that. So this will be the starting point over here. All we got to do is simple, conceptually move this guy here from here all the way stack on top. That's the third phase. It might seem a little bit magic to you, but that's really the nature of the recursion. When I say I want to move this guy here from here to here, I assume I have a solution. That's really the spirit of recursive design. How exactly it's going to work, we'll see that in the trace. All right, in a moment. All right, so this one here, of course, I can just make it purple, so you will see that exactly consistent. All right, one thing to note when you study for the solution, you want to notice that here we got the destination being the intermediate. And also here, the origin being the intermediate. The reason is, when I want to move this guy over here, I want to move that from here into the intermediate. That's why the intermediate is the destination. On the other hand, when I'm here about to start, about to start stage number 3, so here the sub tower here is going to be moved from the intermediate here, being the origin now, into here. That's why I got intermediate here. All right, just notice that. That's something you want to convince yourself as well. All right. Any question? Hopefully, at least the big picture is clear, right? So once you can see, we basically have repeated the strategy the second time already. The first time is when I actually try to demonstrate to you on the diagram about how to solve the problem informally. The second time is when we analyze the Java code. Now I'm going to do that the third time, which is to trace the code. Okay, and I'm not going to do using the call stack. It's going to be too confusing. Nobody can do it right live. Okay. What I'll do instead is to show the high-level tracing, which is going to be beneficial, okay, for you. All right, let's now take a look at the tracing here. All right, and you will also see the solution over here in the slides, but I'm going to do it from scratch, so you can really see the build-up process. Okay. All right, let's now say we got disks over here. That's called the DS. Right, it's a call by value. And let's say we got A, B, and C. We got A, B, and C over here. And also we got indices 0, 1, and 2. All right, let's have some convention here. So the way I'm going to visualize, let's say A is going to be green. And B is blue. And also C is kind of orange. So I'm going to start with C here at the bottom here, and B over here, and then A would be green. Oh, should be smaller. Like that. Okay, that's my starting point. So think about this one here is the original problem. Original problem. And in order to solve this, we're going to see that when we try to show the tracing over here, we're going to see exactly subproblem number 1 and subproblem number 2. That's what we'll see in just a moment. Okay, let's now try to get started. I'm going to skip the starting point here. Okay, let's see exactly how the recursive helper method is going to do. Okay, so let's start right from there. All right, I'm going to call that Tower of Hanoi helper. So Tower of Hanoi helper, I'll say H. And then I'm going to pass call by value the disks referring to here. And then in the beginning, I want to cover the entire array. That means I want to solve the entire problem. It's going to be from 0 to 3. So right here, you can see 0 to 3 is corresponding to A, B, and C. And that's really corresponding to the entire tower. Right away, we can see that. And then where do I want to move it from and to? I want to move it from pack number 1 to pack number 3. In the actual programming, you will say 1 and 3. But let's make it more informative for you on the paper. So why don't I say P1 to P3? Okay. So you can see, even though these 4 things are really all integers, but they represent different things. So these 2 are the range specifying the tower that we want to solve. And these 2 are the origin and destination packs that we want to move from and to. All right. So this is the initial call. And apparently, this problem here is too big to solve. So what we do is we're going to divide that into 3 phases. Phase number 1 and phase number 3 are going to be recursive calls. Phase number 2 is going to be something very quick to be done. All right, let's now try that. So phase number 1 is going to be, also we're going to call Tower of Hanoi helper, and then call by value just the same array over here. And now I want to specify just these 2, the subtower, everything except for the last. It should be basically A and B, 0 and 1. Agree? So it's going to be 0 and 1. And think about 0, 1 is covering only these. 0, 1 is only covering these. Okay, like that. Okay. And I basically want to move from here into something intermediate. Not really to here just yet, according to strategy. All right. So what I will do is I'm going to say from P1 to P2. And one thing to note, P2 over here is the intermediate. And you can think about the P1 over here and the P1 over here. These are the origin. And for later, this one is the destination. Okay, that's the first phase. And we're going to talk about this in just a moment. This one apparently has not reached the base case just yet, because this subtower here is still too big for me to solve right away. All right, how about phase number 2? Phase number 2, we're going to move the bottom one over here to here. All right, so let me annotate here quickly. So also we got subproblem number 1. Right, that one over there, let me just show to you. That one there is about moving this guy over here into here, right? You want to move from here into over here. Okay, that's a subproblem number 1. And for subproblem number 2, we're going to move this one here back on track into here. All right, that's something we'll see later. Okay, let me just put it over here, so that's complete. All right, so what about the second step? Second step, we can simply say move. Since we talk about A and B here, so the one that's at the bottom here is C. All right, so we can simply say move C, and then you want to move that C. So once these two have been moved to here, so we want to move C from the original pack number 1 to pack number 3. All right, so from pack number 1 to pack number 3. Okay, that's phase number 2. And phase number 3 is going to be yet another recursive call. Tower Hanoi helper. DS. Call by value. And then we still want to move a strictly smaller tower here from basically intermediate onto over here. So conceptually, we're going to stack it on top. So think about that's going to complete the puzzle, right? That's what we're going to achieve. That's something we're going to move into over here. So that's subproblem number 1. Sorry, number 2. Subproblem number 2. Okay, so what do we specify? We still want to get A and B. So let me say we're gonna cover A and B, which will be 0 and 1. So we're gonna get 0 and 1, the same size of the subproblem. 0 and 1. So look at 0, 1 here, 0, 1 here. That's okay, the same tower. And then what about origin and destination? All right. If we're here, that's the beginning stage for subproblem number 2. We basically want to move this from here, stack on top into here. That'll be from P2 to P3. Agree? All right. From P2 into P3. And again, notice that P2 over here is the intermediate. And P3 over here is the original destination. Let me do a quick highlight right away. To solve this problem over here, to go from P1 to P3, so P1 and to P3, we have to first go from P1 to P2, P1 to P2, and then from P2 to P3. Right? That's exactly what's showing here. But you want to make sure when you go to the intermediate one, it's got to be a strictly smaller tower. Otherwise, you get infinite recursion. All right. So this one here will be stage number 1 over here, stage number 2, and also stage number 3. So in order to execute this, we need to execute this, followed by that, followed by that. It's a little bit similar to Fibonacci sequence, if you recall. We say, for example, F5 can be F3 plus F4. In order to really calculate this, I need to first calculate F3, which might involve certain recursion here. And then after this is done, I can go on to F4. Similar. You can only get to phase number 3 after the previous 2 phases are done executing. Question, please. I agree. Absolutely. Thank you so much. It's definitely a terrible typo for me. Yeah, this one here should be 0 to 2. Absolutely. Thank you so much. There we go. Thank you. Yeah, for sure. All right, so this is what I'm going to do. I just want to show to you how this branch over here can finish executing. We're almost there. Oh, I said 3 again. Funny enough, I thought 2, but somehow I write 3. This is 2, right? Okay, good. Thank you. When you somehow too much into tracing, you don't really recognize numbers anymore. Thank you. I really meant 2. Okay. All right. All right. All right, so guys, here's the deal. I'm going to finish executing this guy over here, and then give you some idea. And then this part over here, give a try. All right, to finish this part. You can see the solution on the slides right here. Okay. Let's now do this one, just to give you more idea. And this one here is saying we want to move the tower of 0, 1. Basically, this sub-tower over here. Okay. The phase number 1 is trying to move from P1 to P2. So P1 to P2. In order to do that, we need to make use of the intermediate one, which will be P3. All right. In order to move from P1 to P2, you need to use the intermediate P3. All right. Let's now take a look how that's going to work. Okay, so we're going to say Tower of Hanoi, helper, and then call by value over here. So now if I want to move this tower over here, let's say, so bottom one, and then the rest. And we're lucky, the rest here is only one single element tower, only one single disk tower. All right. So that one there, I'm going to put 0, 0. And I want to move from P1 to P3. Okay. This one here tells you I want to first of all move this one here into here. Okay, that's what I will do. And then after that, phase number 2, I want to move the rest. Think about this tower here. First of all, I move the sub tower into here. And then move the bottom part over here into the intermediate one, which is over here. All right. So this one here will be move the disk B, which is exactly over here. All right. B, and then you'll be from P1 to P2. All right. Phase number 3 will be similar. I think once you have got this level here, you're pretty much getting almost everything. I think this one here just further practice. So that's why I'm doing that a little bit more quickly. Tower of Hanoi. So this over here. So the same sub tower. 0, 0. So you can think about 0, 0, 0, 0. It's basically, oh, you know what? I should really use green. 0, 0, 0, 0. Just corresponding to this 0 over here. All right. And then it's going to be from intermediate P3 back to P2. So after all these steps, here, we will have achieved moving this into over here. So think about from here to here, conceptually, it's only one step. But concretely, it's going to be 3 individual steps. All right, that's something you got to pay attention to as well. And this part over here is going to be exercise for you. So this part over here will be some exercise. There will be something you got to trace. And I'm going to make a final comments. So think about how this tracing is going to help you. Since I know that in order to calculate this original problem here, I need to calculate this one first. In order to calculate this one here, I need to calculate 1, followed by 1, followed by 1. And by the way, 0, 0, 0, 0, if you see that, exactly the base case. All right? And this one here, you can think about it is step number 1, number 2, number 3, and then the number 4. And once you do the exercise, you will see 5, 6, and 7. And in order to solve this original puzzle over here, you will just need to follow through 1, 2, 3, 4, 5, 6, 7. All right, that's what you will need to follow. And if you go back to the Java code, over there, you can see no surprise. 1, 2, 3 is something we just traced. You can double check. Number 4 is the phase number 2. And 4, 5, and 6 are the phase number 2. Sorry, phase number 3. All right, some details to be understood. Maybe I got to spend some time understanding this. All right, any question about the tracing here? It will take some time, okay? But if you understand roughly about how things go, you just need to work out the details a little bit more. Oh, just one more thing to say. You might be wondering, oh, how about this method call? Since already reached the base case, so this one here is easy to work out. 0, 0, that means it's referring to pack A. So you're going to move A from P1 to P3. There's no intermediate. It's a base case already. Okay, P1 to P3. And this one here, move A, P3 to P2. All right. Okay, that's about the tracing. All right, so the final thing I want to do about the Tower of Hanoi, this is something that's not going to be covered in your exam. but for you guys' information. So what we have done so far is pretty standard for how we understood programs in this course. We're gonna talk about some conceptual sketch, right? That's how we started with. And also we did the Java code analysis over here, understanding how it is supposed to execute step by step. And then we try to trace some actual program, some example run. What we didn't really do in this course is to analyze how efficient the solution is. And this will not be such a concern in this course as long as your program terminates, we'll be fine. But in 2101, next semester, about the data structure, we're gonna study a catalog of different data structures. Every time to solve a single computational problem, you got simply different alternative data structure you can choose from. Which one should you choose? You should choose the one, number one, that can be correct. Number two, that can solve the most efficiently. So now I'm going to give you some idea about what efficiency really means in terms of time. All right? And I'm not going to touch something well, of course, to do it formally, you got to use the big O and also asymptotic upper bound. Let's not worry too much, right? But I want to give you some intuition. But we're going to need a bit math, a little bit, not too much. All right, so let's say this. Let's make the following assumption, okay? Let's say I'm trying to solve this problem here. Of course, for people working back in India, they get a 64 disks, right? It's gonna be a much bigger problem. Can we make the following assumption? To move one disk from one pack to another, it takes 1 second. Reasonable, huh? Reasonable, okay? For one person, just 1 second. And now the question is, if I give you n disks, can you tell me how many seconds it's gonna take for you to complete the puzzle? For example, let's say for this problem here, if I give you 3 disks, it took 7 steps. That means 7 seconds. So what about 8? We're gonna calculate. What about 64? We're gonna make that conclusion later. All right. What I'm gonna do is I'm gonna make a formula to tell you, given n, I can tell you exactly how many seconds it's gonna take. All right, let's now see how we can derive that. It'll take about 10 minutes. Okay, let's do that. All right, so I'm going to have this called a runtime function, t. Okay, it's a standard notation here. T standing for time, running time, runtime. Let's say seconds. And the input is going to take will be the number of disks. When number of disks is simply 1 second. Move from 1 to 3, right? Simple. What about when it's equal to n? For that one there, we're going to find the corresponding recursive case over here. All right? So you can see we were basically doing recursive case number 1, and also we're doing recursive case number 2. All right, well, conceptually, you can think about, in order to move this tower, I need to, first of all, move the sub-tower from here to here, and then the the sub-tower from here to here, and then the same sub-tower from here to here. I got to do it twice, okay? So you want to think about what's the problem size. So since we talk about from and to minus 1, from and to minus 1, I got exactly 1 less disk to handle in the sub-problem. Agree? So think about the original problem here, which would be from and to. That one there is more like a t of n. And over here is going to be t but n minus 1. I got 1 disk less. This one here is also t n minus 1, the same, recursive call. And what about the one in the middle? This one here is like a moving the bottom disk from one pack to another, 1 second. So if I sum this up, it's going to be 2 times this plus 1. All right? So that's how I work out the equation. So 2 times t of n minus 1 plus 1. This will be something that you guys will have to somehow derive for 2101, especially for searching and sorting algorithm. That's something we'll talk about, don't worry. I want to give you some look ahead. All right, so now I still don't have the formula. I need to somehow derive the formula from here. Okay, so I'm going to do something called unfolding. Okay, so what I'll do is I'm going to start with T of n, the original problem here. That one, by definition, is going to be, let's say we haven't reached the base case yet. It's got to be exactly 1 for that to be qualified to be a base case. So it's going to be 2 times T of n minus 1 plus 1, right? So what I'm doing here is just copy this formula here. This one here is this one here. Okay, the first step is the most critical. Think about n minus 1 is just one instance of the same problem, except rather than n here, I can plug it out by n minus 1. This one here by n minus 1. Right? I'm pretty sure that's something you did maybe in the linear algebra course, right? Something similar. So what I will do is I'm going to say that'll be 2 times something here plus 1. So this guy over here is going to be, I'm going to replace n minus 1 for every occurrence of n. So notice that here it's going to be n minus 1 minus 1, n minus 2. All right. So I will get T of n minus 2 and then plus 1. Okay. Oh, I'm missing something here. Apparently, I'm not very good whenever I talk about number 2. And don't forget, there's a 2 here. All right, that's precise. All right, let's unfold one more time. The reason that I still want to unfold is because n minus 2 is still too big. I haven't reached 1 just yet. Okay, let's do one more. So what I will do is I'm going to actually talk about unfolding this guy over here. What I will do is I'm going to substitute n minus 2 for every occurrence of n minus 2. So that means n minus 2 minus 1, n minus 3. Right? So I'm going to do this 2 times plus 1 plus 1. All right? And I'm going to fill out something here. So if I replace it, it's going to be T of n minus 3. Again, I forgot about 2 times. Right? Don't forget, there's also 2 times here. 2 times n T of n minus 3 plus 1. Okay, now you cannot just keep unfolding this indefinitely because it wouldn't get anywhere. As soon as you have unfolded the running time formula there for a few times, now your job is going to observe some pattern about how the unfolding can potentially reach the base case. Okay, I'll give you some hints. As you can see, we got 3 here, right? Coincidentally, here, 2 times 2 times 2. 2 to the power of power 3. Plus 1 plus 1 plus 1. Plus 3. Somehow, this number here corresponds to exponent and the constant factor over here. Somehow. I can verify this again. 2 here, 2 times 2. 2 to the power 2. Plus 1 plus 2. You can see 2 here matches 2 and matches 2. And also 1 here, I got 2 to the power of 1 plus 1. 1 matches the exponent and also the plus 1. Looks like a safe pattern to conclude. All right, so this tells me every time I try to do unfolding for one more time, I'm going to reduce the n value by 1. So I go from n minus 1 to n minus 2, n minus 3. Now I want to ask myself, how many unfolding do I need to do? N minus question mark over here is about the number of unfoldings. I want to reach the base case 1. So this is the most critical number to work out. Any idea what the question mark should be? N minus something is going to be equal to 1. Guys, that should be easy mathematics, right? I'm pretty sure you know. You're just shy. Go ahead. Just n minus 1. Yes, that's correct. All right, I'm pretty sure you guys know, right? And what your classmate said was also correct. Right, double check, right? This will actually work. This one tells me that I can say 2 times 2 times 2 all the way to, I can eventually get to t of 1, and then I can say plus 1 plus 1, plus all the way to 1, something like that. Okay? So this one here is the base case. I know that it's 1. And this part over here, I know that the number of unfoldings I need to do is n minus 1. So that should be 2 to the power of n minus 1. All right? And this part here, also I know that that one should correspond to the number of unfolding as well. That should be plus n minus 1. All right, let's now write this aside and make a conclusion. Since we have done so much work. Ultimately, this one here is going to be 2 to the power of n minus 1 plus n minus 1. This is to say, if I tell you I got n disks in the Tower of Hanoi as an input, it will take this much second to complete the puzzle. Right? Of course, you can plug in some specific number. We'll do that later. Okay, so now, for those of you who took 1019, for example, you learned about big O, just for your information, we can drop this term here because asymptotically, exponential is going to dominate over linear. That's something we'll talk more in 2101. But you can say this one is approximately 2 to the power of n. Approximately. Okay? All right, so let's now make a conclusion. Let's go back to the puzzle, right? So what we have done in terms of mathematical analysis can really kind of answer our doubts about when is the world going to end, right? That's the question we want to ask. That's a Java code. That's the unfolding. That's the running time. All right, back to this legend here. Oh, we're making the assumption 1 disk take 1 second. And since we got 64, so now it should be 2 to the power 64 seconds to complete. Any idea how long this will take? Quite a lot, actually. It takes this much time. More than 5 billion centuries for them to complete. So I think we are fine. It will take them quite a while to finish that. So don't worry, you can still finish your exam on Sunday. All right? Not a concern. All right? Anyway, so that's the Tower of Hanoi. For the exam, you don't need to worry about the mathematical analysis I just went over. Don't worry about it. But that one there just give you some idea about what you have to do in 2101 next term. Okay? This one, don't worry. But what you should really spend some time is about tracing and also the Java code, since we covered that. All right? That one I'll leave to you. Okay? I got 16 minutes. How about we take a 2 minutes break very quickly? I just got a few slides to wrap up the course, and then we do that. Whatever time we got remaining, I can maybe take questions from you. If you got about the exam, about the course in general. Okay, 2 minutes break. All right, so before the break, we kind of finished that final recursion problem. Okay, so, there's one thing I forgot. Okay, I'll mention very quickly, just a few seconds. So that's basically the last slide. And don't forget, I made available the lab on the recursion for you. I went over one problem already on Sunday, the tutorial session. You can feel free to explore more. And also notes on recursion that can summarize how we think recursively. And also the API for string. I think this one might be less important, but I'll say just know about how to use a substring and also char at. That should be enough. And also coding bat, right? So try it out. And for those of you who want to spend extra time beyond this course, functional programming language. That's my best advice. All right. Okay, let's wrap up the course. Basically, nothing special. I just want to maybe enumerate all the topics that we actually cover in this course. May not be exactly exhaustive, but I think most of the important ones are there. Just go over them with you just to see how much you really have achieved, how much you have learned, and also give you guys maybe some ideas about how you can try to invest your time to sharpening your program skill. Okay, so we have done some procedural programming. For example, exception. So exception itself is more about tracing the call stack, right? About the caller and callee. Strictly speaking, it's not exactly object-oriented, but it's foundational. And of course, recursion that we started covering focus more on the recursive thinking, because once we get to 20101, we are actually going to raise up your thinking level rather than on the array, which you might still do a little bit in the beginning when we brush up the material about recursion, but we're going to think recursively more on the non-linear data structure, like a tree. That's something we'll talk about maybe, maybe in January, if you're taking the engineering section with me. And then also implementation in Java and also tracing, right? So we talk about two tracing, either using a call stack or the high-level tracing. I would say for more practical use, high level. Data structure, only one, just the array. However, in 2101, I'm going to dive into more insights into manipulating the array. Especially, we never talk about what about you want to grow the size of the array. For you guys to take a guess, right? You don't need to tell me the answer. Let's say I want to grow the array. There are two choices to me. Either I can say every time I want to grow the array, I grow it by doubling the size. Or I will simply grow by some constant number of elements. Which one is going to be more efficient? That's something we'll try to solve as well, mathematically, in 2101. Anyway, so for 2030, just the arrays. And then OOP, we talk a lot. Classes, attributes, reference data types, right? That's really the OOP review. And all kinds of methods. And for the helper method, if you recall, we talk about it from two different angles. So in the beginning of the course, we talk about in order not to make your code smell, you want to remove duplicates by calling helper method. And when we talk about recursion, we talk about some special term called recursive helper method. Nothing special, just a helper method with a recursive nature, right? We still want to reuse the code. Especially for recursion, you just want to make sure you're passing some strictly smaller problem for each recursive call. Dot notation, aggregation, right? We talk about how to navigate between classes using the dot notation. Context objects, aliasing, for sure. And then inheritance. We spent quite a bit of time studying it. So we started by code reuse. So we talk about different design, single choice principle, cohesion, right? So these are some design principles for you to also take home, take away from the course. Expectation, once you got a static type, you should know the expectation. So we got a substitution rule. When you say want to assign X to Y, what should be the rule, right? And we got static versus dynamic types. And also we got polymorphism, dynamic binding. So these two are arguably the single most two important topics for inheritance. Everything actually kind of lead themselves to there. For polymorphism, we got polymorphic method parameters with call by value. And also we got polymorphic collections like a polymorphic array. Just got to review how we build it. And also polymorphic method return values, right? We'll talk about all these. And we talk about typecast. What does it really mean to be compilable? And also how we can run into class cast exception and how we can avoid it using instance of checks, right? And overriding, dynamic binding, and we talk about specifically for equals method. And you should really always find the closest ancestor for the overriding version. All right, so we'll talk about IDE. We happen to choose the Eclipse to use in this course, but you can feel free to go beyond with your own efforts for other IDE, IntelliJ, whatever, Visual Studio. And breakpoint debugger is really universal. That's something I really want you to get used to. System.out.print line is not going to work in a large-scale projects. It's got to be breakpoint and debugger. And unit testing, we have done a lot since day one. And also test-driven developments, regression testing, also everything that we have been doing in the labs, and also the programming test. It has this flavor. All right. The only thing I didn't really manage to cover in this course would be something called generics. It's something relatively popular topic for sure. In 2101, as soon as you get your either the first or second programming assignments, you will be given some background study about generics. That one there, once you learn about inheritance, it's not difficult to really pick it up. So for those of you who may want to take a look at what it is, feel free. I got learning resources for you. Of course, it's not on the exam, right? Don't get me wrong. That's only for you to consider. Generics. All right, so beyond this course, this is just some recommendation. It's a book on algorithm. That's something usually will be used by your 3101, the algorithm course. You can take the book, and there are so many interesting algorithm for you to go over different data structure. And the good thing is they put so-called pseudocode not in any programming language in the book. You can translate it into Java and write some JUnit test cases about it. What can be a better way to train your Java skill than this, right? It's not going to be done in a month or even in a year. It's a long-term investment. Okay, for those of you who might want to dedicate, you can consider. And this is even more relevant to 2030, which we didn't get a chance to cover. It's something called design patterns. You might get yourself exposed to it more in 3311, software design course in the third year. Basically, everything we learn about inheritance is going to be used in almost every pattern over here. Design pattern simply means you got different scenarios for your design for you to solve. And each scenario might require a different nature kind of solution. So they kind of talk about it. The book itself gives you a solution in C++, but why not translate it into Java? That's another good exercise. It's a classic book, actually, on design patterns. All right, final slides. So in 2101, we're going to assume you have learned all these programming concepts, inheritance from 2030, and then you're going to need also the math you learned from 1019 or 1090 very, very closely. Well, we're going to need that for sure when we do some analysis. So logic is going to be your friend, not your enemy. Okay? And try to keep practicing Java. All right? And that'll be it. All right? Thank you. That'll be it for the course. I appreciate it. Thank you so much. Okay? Thank you. All right. Guys, thank you so much. Again, I appreciate it. And now, I got 5 minutes. Any question you want to ask me about exam? How hard it is? It's going to be more challenging than your written test. So, but I would say what you got to do is make sure really go over the stuff that we talk about in class. It's going to require you to really show your understanding for certain questions. There will be some standard one. There will be some tracing, but there will be some questions that require some short answer, which will be require some thinking. Okay, there will be. Yes, labs is also possible, but you don't need to redo the labs. I would say just go over the solution you have, maybe either from my standard solution, from your solution, to go over the critical method, just get some idea about how to implement stuff, right? But make sure you definitely will get recursive helper method to program. I know you're gonna ask. So I'm still finalizing, I'm not lying, I'm still finalizing the question here. For now, I got 20 multiple choice. I got about 10 written questions. Okay, just for now. So if you see something different on Sunday, please don't quote me on that, right? I'm still finalizing, right? You might get more written. Multiple choice, maybe 20, that'll be it. Okay, 3 hours, yes. It's going to be covered, yeah. So I would say for abstract classes, interfaces, as I said, you don't necessarily have to watch the video. You don't need to. Maybe go over the slides, like made available to you. If there's any part you're not exactly sure, either watch the video for that part, or just reach out to me. I can explain to you. Yeah. Question somewhere? No. Good. Definitely not multiple choice, right? You just basically put on the choice. I think for written question now, they quite maybe about 2 or 3 only for now. There will be certain part you're gonna read some code fragment there to understand how it is supposed to do, and then you're gonna fill out some blanks. Anyway, you'll see. You first, yeah. The practice problem is already on the lecture side. Yeah, since 2 days ago. Check them out. Question. Okay. For now, for all the multiple choice I got, only one answer that's correct. If the multiple choice got multiple correct answers, I'll let you know explicitly. Okay? Okay, so just in case, let's say for the multiple choice, there are multiple correct answers. So the marking scheme is going to be the same as E-class. Yeah, just the same. We're not creating a new scheme. Yeah, go ahead. Again, I don't want to lie. They are easier than the actual exam. Okay, so you guys take that as one way to familiarize the format of the exam. But I would say the inheritance question there is closer to the exam. I think the alias one is pretty straightforward, right? Maybe for the inheritance one, you will definitely be asked to give an Java class declaration and draw the inheritance hierarchy, right? That's something you gotta make sure you do. And then once you get a hierarchy there, you gotta understand whenever you're given some variable assignments, how would that compile? And also, if you do any typecast, when would they compile? When would you get like a class cast exception, right? Just review those. All right, thank you so much. I still got office hour today, and also Thursday and Friday we got a review session, and then otherwise I'll see you on Sunday. All right, take care.